Welcome to Ask the Expert Live, the show where we answer your questions about the gear industry. Today our topic is gear design, and I've got assembled here a panel of experts who will answer any questions you have on the subject. But before I get started, I just want to say that if you have a question in the audience, please just raise your hand and we will hand you the microphone. We encourage you all to participate. And with that being said, I'd like to allow the gentlemen to introduce themselves.
Thank you. I'm Ulrich Kissling. I designed the software KISSsoft for gear design, and let's say I started my career in a gear manufacturing company, but then I learned a lot by the user of the software. So I'm here.
Very good.
Yeah, hello, I'm Karsten Stahl. I'm professor at the Technical University of Munich and director of the Gear Research Center in Germany. We do any kind of research on gears, so any type of gears, spur, helical, hybrid, warm gear, in any kind, efficiency, strength, and noise vibration harshness.
I'm Frank Uherek. I'm principal engineer with the Rexnord Gear Group. I've been involved in the gearing industry since 1980. I've designed gears that you can hold in your hand and gears that weigh 220 tons. I've also designed gears that run as slow as 2 RPM and as fast as 36,000 RPM. So I sort of covered the gamut, and I'm looking forward to your questions.
All right then. I'm going to start with a question from one of our readers, and it starts this way. There's been an interest in asymmetric gears recently. A number of publications and books came up. It seems to be one of the last frontiers to optimize cylindrical gears in terms of geometry. Is there a wide enough use of asymmetrical gears in the industry? Are they becoming, and will they become more widely used? And do you believe the use will justify investment in cutting machines and tools, or will they remain a niche?
Maybe I start with this. I think both gentlemen will have something to add. Certainly, asymmetric gears will have advantages. If you have an application with a main direction, like a crane pulling only in one direction, you can optimize one flank for the purpose, which is definitely positive. But on the other side, the questionnaire said you need special tools. The second thing is you need a specific calculation, and you're leaving the standardized methods. And this will make life very difficult. And both reasons in these days did not overcome the advantages. So most customers still stay with symmetric gears. Mm-hmm. In future, I think we will introduce asymmetric gears in calculation and standardization. This will give a push to asymmetric gears.
Anybody else?
I agree. The cost is a very important factor for asymmetric gear, but for example in plastic, where you produce the gears in stamp, there is basically no cost increase. So there it's very interesting. And you can, when you use a higher pressure angle, you not only reduce head pressure, you reduce losses. And that's important today. The calculation part is not very tricky. We already introduced asymmetric gears in loaded tooth contact analysis, where we improved the Weber-Banachek rule, which was developed in his institute to asymmetric. It's easy to test because you can check it with finite element, mm-hmm. and we also had to change in the calculation method for according ISO for symmetric gears. The bending stress is different, and the stiffness of the mean stiffness in the meshing, but both parts are already in research and documented. So,
Frank?
I think the asymmetric gears have a fantastic ability to solve a critical problem. And if you have a problem that you need a solution for high volume production, so you can cover the cost of the tooling and have an application, as you had mentioned, that's single rotation, they're absolutely fantastic. If you're going to make one-off specials, tooling is tough to get. And and perhaps something with additive manufacturing that gets rid of the challenge of the tool would probably make those gear more common for a one-off type of use.
All right, thank you. My next question is, it's a little bit long, so bear with me. Closed loop is a concept widely talked about and being implemented in gear manufacturing. What about closing the loop between design, manufacturing, measuring, and then reassessing the performance and properties of the gears as measured? Meaning to feedback measured gear data into the design tools, such as gear software. Is there a need to analyze the gear performance using real gear geometry data? Is it a requirement, for example, to analyze the transmission error, considering the manufactured surface structure and considering manufacturing errors?
I can try to make a start. It's not one question.
Yes, it's many
several
questions.
Starting with the word closed loop. I think this is coming from the bevel gear production and the bevel gear development cycles. Bevel gears have a much higher deformation during heat treatment. Therefore, this is required, that you have a fire check and you push back the data into the soft parts. In cylindrical gears, the demand for that is not so high. So due to the form of the parts, the deformation is not as high as on ring gears with bevel gears. And therefore, this called closed loop process is not required in the same way. Nevertheless, all manufacturers are doing something like that automatically. So when you control the stock and you see the grinding areas not becoming clean, others have too much stock removal, they will adjust automatically. So I believe that the process, the closed loop process, is already in place, but not under this name.
Go ahead.
I think closed loop is very critical if you have high series production. If you're going to make 100 or 200 gears of a kind and you start out with your first gear and you find out, hey, it had a little more distortion and heat treat than you wanted, you can then go back and make gear 3, 4, and 5 and adjust and try again. If you're going to make one of something, and you come back and the quality assurance lab comes back and says, hey guys, you didn't meet AGMA 10 quality. Okay, you've warned the engineer to figure out how to recalculate the ratings to see does the gear still work, but you don't have that second gear to fix. So it's more of a case of if you have long run series production, I think it's incredibly valuable. But one-offs, it just warns you that you got a surprise.
I think the demand, it's absolutely clear that closed loop comes from the bevels, and now it's now actually in the last maybe year, it's very strongly coming also in cylindrical gears, and actually it's a little bit theory, but I see one possibility that it should be possible to get the final measured gear data back into the design software and then run maybe a contact analysis to see what is the difference. And I think this is something we will have to develop in the next some, I don't say years, maybe months, that we have. But if you get measured gear data, it's horrible information because it's like this, and when you then run the contact analysis, you don't get any results. You have to smooth it to see the trend, and then you can use it. So I think this is something which is not too tricky to do in software, and then we will see how good the effect in practice is. Maybe for single production, if I have a gear model 30, I will not throw it away, and maybe I can not do an additional grinding. When I see I'm out of tolerance,
Right.
and see what happens. For that, but for mass production,
Yeah.
Thank you, gentlemen.
Maybe there was some question also about roughness. And I think in addition to what I said before, it needs to be separated. The quality of a hard finished part needs to be adjusted in the manufacturing process. When you now have too much stock or too less stock, then you need to adjust the soft part. And this is very much different. This is only production process. At the end, you have an AGMA 10 or ISO 4 or 5. Everything is okay. Different is when you have lap gears, for example, without hard finishing. Then you need the quality in the hard part, and then it's urgently it's required that you have this fire check process.
Okay.
And we don't have this in cylindrical gears in the same manner.
Thank you. ISO standard 6336 has been revised, extended, and renumbered. How closely does the industry watch this process, and will this process create an interest or confusion once all parts of ISO 6336 in the new revision are released? Who wants to jump in?
So the ISO Working Group 6 will take place on Thursday and Friday this week, and I'm convener of that. So therefore, please allow me to start with,
By all means.
with the answer. We made a great effort to collect all parts together and put it under the roof of 6336, targeting to make it easy. So we have a numbering system which makes it easy to understand, is it a material related damage? And also higher numbers for example calculations. This is a small family now, which is brand new, and end of this year it will be released. We are pretty sure that Thursday, Friday we will make good progress, and we are convinced that this will make life easier. The small family is starting, and then we will collect more standards, more technical reports into this roof of 6336, where you have one area to search on cylindrical gear strengths, and you will find everything in there. I hope that industry is following and will be happy with that. I would be very surprised if the applicators of these standards will be disappointed. I hope it's positive.
The AGMA Helical Gear Rating Committee has been doing is they serve as the technical advisory group to AGMA and ANSI to TC60 to your committee. And the Helical Gear Rating Committee has members of industry. You know, it's a very practical oriented committee, and they spent a huge amount of time looking at the change that was proposed to combine these documents and have them all under one umbrella. And one of the items that they felt very strongly about was to have an explanation in the text to say, okay, your first 5 parts, the initial rating practices, those are standards. The other items that talk about tooth flank fracture and micro pitting are technical reports, which basically means the industry is saying this may be the way we should do some calculations, but it hasn't been out in the field that long, so we want to just try it and see, but it doesn't have the force of the standard. That, you know, if you're rating gears to ISO 6336, you basically need to follow Part 1, which is the general standard, Part 2 for flank or durability, Part 3 for strength or root, Part 5 for materials. And the other items are a combination of example problems, so it gives you a way to check your code to say, hey, I've written a computer program to the standard, does it work? Well, here are some examples. So in summary, I think industry is following it very closely, and I think they appreciate the fact that it's all together in one package, so it's just easy to access the information.
Probably the question was mainly about the part 2 and 3, part 1, 2, and 3, which is since long time used in the industry. And there we have a lot of very small things changed. We did the calculation examples, FTG, KISSoft, and we had differences. And we had to figure out why these differences, and it was interpretation of some notes in the standard. So all these things were worked up and make more clear, so that basically the new standard should be more clear, so that everybody follows the same rule. And few things are really changed. One thing is for internal gears, there the bending strength will be quite different, but comparing with finite element, much more precise. I don't say we get lower safety factors, but we get different safety factors. And then there are some other smaller things. We will not have a big change in safety factors. That's always the problem. When you have a new standard, you calculate your existing gear, you have nice safety factors, and you tell your customer we are okay, over 1.4 for the, and then with the new standard you are down to 1, and then everybody cries. And this will not happen with this new standard. So this helps also for acceptation.
Very good. Besides the gear rating along ISO or AGMA using engineering formulas, do we need another or new approach to strengthen life analysis of gears? For example, based on a finite element analysis. Are the standard-based ratings accurate enough? If not, what are, besides testing, alternatives?
Why is everyone looking at me? That has been under discussion in the AGMA Helical Gear Rating Committee for a couple of years. And a lot of people will come in and say, hey, we've got a new finite element analysis method, and they'll model the root fillet, and they'll put the load on the set, and they say, look, I've got this gear, and it's red, and it's green, and it's blue. I said, well, okay, that's nice. How much output torque can it transmit? Well, it's red, and it's green, and it's blue. And what we haven't been able to get is to translate the results of an FEA analysis into, kilowatts and Newton meters, horsepower and output torque. And so, in terms of that, that's a challenge. The other challenge we have is trying to calibrate our rating methods. Right now, both in AGMA as well as ISO, we say you need to have a steel gear and it needs to meet a couple of properties, but it doesn't give you any advantage if you have this alloy or the other alloy or this alloy. It just says, no, it all rates the same, even though we as gear engineers know rate's different. Is there a better way to validate? Well, yeah, you can do simulations. There's been extensive work on simulation software that models the vibration and the noise response and the efficiency of it. But then, of course, you have to say, well, could you prove? How do you know the software is correct? Well, the old saw is if it prints out on green bar paper, it must be true. I don't buy that. And testing actually is the best way, and that's how standards were developed. We went into gear laboratories, we tested gears, we saw their performance, and then we extrapolated out and wrote a gear rating standard for that. So FEA, I think, can be used in specific failure applications when you're just sort of, what's going wrong? But then trying to take red, green, and blue and put it into output torque, it's not there yet.
I completely agree. I think the purpose of a standard is not to be most accurate and exactly fulfilling the physical behavior, but to repeatedly lead to the same result. If two persons calculate according to DIN to ISO 636 part 3, they should come to the exact same result. Mm-hmm. That is the purpose of the examples too. Mm-hmm. With FEM we have two issues. One issue is that not every calculation is the same. It depends on the characteristic, on the element size, and many other parameters. So before doing that, we would need to standardize the FEM calculation to get the right colors.
Right.
Because even the colors can be different. And second is now to get the notch sensitivity, statistics, the behavior of when some small area has high pressure, it will yield and other areas will carry. This all is covered in the empirical approach of the standards today, and it would need to be covered in a new standard for FEM.
Yes.
And we are working, we at FZG and other institutes are working intensely on that. Now we need to put everything together and agree how we want to get this into an international standard. This will be something we will have to start discussing Thursday, Friday, and this will be something we need to consider, yes.
I fully agree that FEM, some people still think that FEM is precise and ISO rule is on the very safe side, and that's exactly not true. You find five FEM guys, with every has another FEM software, they will have a variation of results which is very high. So we have to be very careful, and I agree. If you would have to dispute on FEM calculation, if the gear is okay or not okay, you would never find a solution. If you say, okay, we agree the standard has its limits, but it's a rule and we look for that, then we get the solution and we can say yes or no.
Okay, thank you. Obviously, the more a gear designer knows about gear manufacturing, or vice versa, the better. Does a lack of gear manufacturing know-how hinder the design and development of geared products in the industry? Who'd like to start?
Of course, certainly. If you don't know how to manufacture, how can you design a gear? You need to know what quality, what capability, asymmetric, for example. You can design asymmetric gear very easily, but then you have the problem of manufacturing. You can print in the drawing low roughness. If you don't know how to manufacture, you won't get it. So certainly there must be a link. There is a link today. There's no gear designer having no clue about production. I think this is more important, that the gear designer knows about production. Of course, it's beneficial if the producer also knows a little bit about gear design, but the other way, in my opinion, is much more important.
Do you think that situation is getting better or worse?
I don't see much of a change here. Of course, the manufacturing process are getting more sophisticated, more complex, more varieties. And therefore, the demand on knowing more for the gear designer is higher. But I don't see a trend here that gear designers know more or less about manufacturing.
I think the major change that's happened, at least over my engineering career, was in the beginning, the design engineer would make the drawing and put some tolerances on it and throw it over the wall to manufacturing. Okay, guys, you make it, don't bother me. I have other things to do. And I think today, not only the change in technology, but just the change in cooperative manufacturing, of getting the designers to talk to the manufacturing people and say, look, I need this tolerance. And the manufacturing people says, okay, we're going to make 10 gears. We might get one right. No, you can't do that. I can't afford that. So I think it's now becoming very common, actually, to involve manufacturing drawing process where you can easily make a change by erasing a dimension on a drawing versus sitting in the shop with a pile of forgings and say, darn, it's not going to work. So, and I think it's incumbent upon gear manufacturers to get their design people out on the floor. If to address even the simple thing of saying, when the manufacturing people call up and say, we had a problem, they'll know how we can fix it. What sort of machines, what sort of techniques, can we do grinding, can we do honing, can we somehow improve the surprise? So I think, a long time ago, no, there was little interest on both parties. And I think today the technology has driven them much closer together.
Yeah, let's say I'm a little bit more pessimistic because clearly we see a lot of companies, and there is sometimes a real gap between who designs, and the designer is in stress, and then it has to be finished, and he will not go back and change things, or even worse, you design and you let produce your pieces outside, and then your guy who is buying these things, he says it's horrible expensive, and things like that. So but now as we are joined Gleason, clearly we got the job to try to add as much manufacturing know-how in the design software as possible. For example, check if power skiving is possible or not. And what I see is that already the language between who is designing and who is producing is sometimes like Chinese and German. It's hard to get things together, but it's clearly a trend that that we have to go this road, that we find if we will find a more competitive solution, we have to join manufacturing know-how in design software, and clearly also help the designer that he knows the problems in things. I think I agree it's an upcoming trend, but I think we have a lot of many kilometers to do.
So how far along in the process are we in that integration, and what are some of the things that still need to be done to connect the design and manufacturing through software?
Yeah, I can give you an example. We have a nice tool which can design with 2-3 clicks a complete gearbox. 3 stages, and then we can design a variation of gearboxes. And then my idea was all the gearboxes have the same power capacity, but not the same price. So I wanted to add in the design software somehow a price calculation. That's what I did is I put a factor for a gear, dollars per kilo, but that's the most primitive you can do. At least you get some results, and you can compare maybe two different but to get a more precise information, I started talking with the manufacturing guys, and they had 50 questions. So I cannot answer 50 questions just to get a simple price. No, so there's it's a longer way than we think. It's not that easy because we cannot. The final process needs a lot of information, which the designer doesn't have or doesn't know and doesn't have the time to do it also. So we have to find a compromise to get good results without asking the poor design guy too many questions. That's not easy.
Will high contact ratio gear forms eventually supplant conventional tooth forms in new designs? Anybody?
Well, I mean, high contact tooth forms is where you have more than 2 teeth in contact during the meshing cycle. So they tend to run quieter. You get a very smooth load transition between teeth because you're sharing that load across another tooth. The challenge becomes to get those high contact ratios. You may have to change your geometry to perhaps use very high helix angles, use very fine pitch, and then you start running into, I have strength problems because I have very small teeth, or I have bearings that are exiting the housing because the thrust force is too large. And, again, I think it's a tool in the gear engineer's toolbox to address an issue from noise or to address an issue of smooth operation that high contact ratios play a role. But if you're looking at crushing rocks, not interested. It just there's no inherent advantage of a high contact ratio in that specific type of application.
I think it's not new. When I did my diploma thesis, I studied Rouverol gears with a contact ratio up to 3 in the face. So it's a standard knowledge. You can easily do that, but what you have is strength issues, thrust issues, and also friction. So the higher the teeth, the more friction. And the trend today, as I can see in mobility, in every application where CO2 or efficiency is an issue, the teeth are becoming smaller. So the demands on quality get higher, and on good layout, they can compensate with a good layout, with a good macro and macroscopic layout of the teeth, the reduction of the contact ratio. I do not see a trend towards high contact ratio.
I see the same. We have a very challenging task in the future for electromobility to make gears much lower in noise, and clearly high tooth is a way, but exactly with batteries we don't have energy and then we have more losses, so it's somehow a big contradiction. But I think maybe the best is to go under load up to contact ratio of 2 and apply nice profile modification, and then we...
One exemption might be plastic gears. Plastic gears automatically come with high contact ratio by deformation under load. So this clearly helps plastic gears for their good noise behavior. But in the initial design, they have normal contact ratio in between 1 and 2.
Are high contact ratio gear designs covered by the standards?
Not really.
You can calculate, yes, above 2, but the experiments are mainly done on 1.5 to 2.0. So yes, you can calculate, but the accuracy is not very high. But it's also a question of the system. The higher the contact ratio is, the more effective the modifications become. So it becomes more difficult to standardize.
I think with the actual ISO standard, if we are above 2, we are on the quite safe side. There's one factor in the ISO standard for high tooth, which was introduced by Mark, but this is irreal because it's only valid if the quality is 4 or better. So I don't know how many gears we have with quality 4, so basically we can forget about. I think there would be a need. Let's say if we say that high tooth contact ratio gears is not more anymore the trend, that I don't see a big necessity that we introduce it in the standard, but clearly I think the standard is I call it on the very safe side.
Good, thank you. Next question is, will rating standards become more nuanced with regard to material selection? Material selection and standards. Will the rating standards include more materials and options?
So talking about metal, I think about steel, the part 5 in ISO will be worked on continuously. So it does cover quite a lot of material range. Also in the DIN mirror standard, we are going to introduce more material and improve the density of material properties. which will then possibly go back to the ISO again. So I think there's a continuous work, not a jump, a continuous work to fill the gaps in ISO 636 Part 5.
Are there gear materials that are being used or being proposed out there that aren't covered by the standards?
But mostly in smaller gears. For example, stainless, rostfrei has stainless steel. You make like this, or other special types. But still, these are not the if you are talking about automotive or industrial gearboxes, then we don't use this type of materials.
Carburized steel is clearly the focus. Inductive hardened steel is difficult. Through hardened steel is not so strong, and special steels are really not in the focus of Part 5. No.
I think one of the issues with special steel is from the standpoint of it's a little bit of a chicken and egg. You know, you have a steel mill that'll invent a wonderful steel, typically named unobtainium, that you can't afford, but it will solve all your gear problems. And the gear engineer says, well, great, what's the allowable contact stress and what's the allowable bending stress? And the steel guy will say, well, the tensile yield is this, and the ultimate, that's not what I asked you. And to get new steels into a standard, you sort of have to figure out what is the gear allowable stress numbers. And unfortunately, their stress numbers, they're not traceable to a steel property that most people can measure in a tensile test. And so, you know, part of the issue is expanding what are the inspections that we need to make sure we don't go into a danger zone using steel of, you know, lesser quality than it should be. And part of it is, okay, if you have a super steel that you want us to use, as was stated earlier, we're writing standards. So we're not going to be at the bleeding edge of technology. Run some tests, do some endurance items, plot a stress cycle curve, and then we can use that data to generate allowable stresses and put into the standard. So I think that's basically where we are at this point.
Okay, thank you. My next question is, will face gear rating methods be standardized?
So when we are talking about ISO, there is currently no plan to do so. We have some calculation methods available, and at FZG we are currently doing more research on face gear calculation methods. Plus FEM you can calculate, but it's not standardized in ISO, and currently it's not on our to-do list. Maybe we have to add on Thursday, but currently it's not on the to-do list.
The problem is when we want to standardize something, we need before that some research is made, a lot of tests and things, and I don't see any, I don't know about anything actually, or very little, so we don't have the material. On the other side, I have to say, if you look how we calculate the bevel gears, what we do is basically we take a bevel gear, we calculate a so-called equivalent cylindrical gear, and then we go into the normal cylindrical gear calculation. And to do this with face gear is relatively simple. So that's how we do it in the software. There was some publication of Netherlands company, Crown Gear, which failed many years ago, but they did some research and they proposed some calculation method which is quite okay. Basically, you take you transform a face gear into a pinion rack, and then you do the calculation. And that's clearly not wrong. It's maybe not so precise, but still it's workable.
I think again in the area of face gears, you know, it's sort of the market needs to demand a standard, and there needs to be applications for it, and then the standards committees can catch up and develop a standard. And right now, I know there was some activities probably about 2 years ago I think there was a paper presented at the AGMA Fall Technical meeting about face gears, but it never really went anywhere. And it's just because, you know, the market demand is saying, hey, if we have an application for a face gear, we're going to do testing, and we're going to, you know, we don't need a standard. We'll just prove, yes, it works in our application, and then use it and move on.
Mm-hmm. Okay, thank you. Induction hardened gears often have an area just below the case core boundary where the core hardness is lowered, called overtemper. What can be done to mitigate the hardness drop?
Induction hardened gears. And I say that humorously. Obviously, there are some tremendous advantages for induction hardened gears. The challenge becomes when we get to a large pitch, a long tooth, and the inductor can't reach down into the root and harden not only the flanks, but also the root of the tooth and come back up again. So you get I think Bob Arakello has called it a metallurgical notch, just like a stress concentration factor. And, you know, how traditionally AGMA rating practices have dealt with it is we just derate the induction hardened gear that doesn't have a fully hardened root. We may be looking at stresses for a non-induction hardened through hardened gear that may be around 45,000 pounds per square inch. And if you take that same material and you just induction harden it and you don't induction the root, the bending strength suddenly drops to 22,000. So we've damaged that gear. Well, but you're induction hardening not for strength, you're induction hardening for wear resistance, and you're in the coarse pitch area. So in terms of trying to deal with how do I get rid of that metallurgical notch, it's basically you've got to figure out how to continuously harden the root fillet of the tooth, or don't do that.
Some research on induction hardened gears, internal and external, with single flank induction hardening and multi-frequency. The potential is there. If everything is perfect, you can get strength nearly to carburized gears, and the potential in production is perfect. So you can pull parts through the production, which is brilliant, but it is not controllable, it is not safe. And therefore, currently, we would not suggest to do induction hardening, but we do more research on it, maybe with modern tools, modern multi-frequency tools and checking methods and standards to test the effect of the inductive hardening. We can get closer to a controllable quality.
Okay.
I agree. I fully agree. One thing which I'm missing in ISO 636 Part 5 is exactly what you say, that in ISO, if the rounding in the root area is not hardened, I always have a lot of people asking me what should I put there, and it's very hard to give an answer. And this would be a nice thing if you had some information into Part 5.
Thank you. I have another induction hardening question here. Induction hardened gears have a steep hardness gradient relative to carburized gears. How much deeper should the case step be for induction hardened gears compared to carburized gears to avoid subcase fatigue?
Yes. The short answer is take a look at AGMA 2101, helical gear rating practice. We have recommended case steps for both carburized and induction hardened gears, and they're set to ensure that we have the point of maximum subsurface stress inside the case of the induction hardening, and that would address the issue. I don't know what they're doing in ISO at this point for that question.
Clearly, it's the same answer. You calculate the maximum of the stress ratio to the yield capability of the material, and the depth should be high enough that it is on the outside and not on the inside. a number. The question was about what should it be. I think yes is the right answer.
Very good. Is there an industry guideline for the optimum case depth for carburized gears to avoid macro pitting?
The typical approach is 0.15 to 0.2 times the module is an area which is very reliable.
There is some 5. But let's say clearly this, there are a lot of rules, and we collected them. There are rules also in HMA, and we collected them, and in our software you can click a button for a proposition, and you see it's a huge variation. So it's clearly it's our rules. Maybe something a little bit better I learned from a German company producing very huge gears, that we use the Hertzen law to calculate the stress in the tooth form, and with that you can adapt a little bit, see if you can reduce in case of needed. But it's a bit more complicated, not just a formula.
What we're doing right now in the AGMA Helical Gear Rating Committee, we're in the midst of issuing a new revision of it, and the committee has dramatically expanded the number of ways to calculate case depth. And basically it's going to give you advice on case depth at various locations of the tooth, either the tip of the tooth, the pitch line of the tooth, or the root of the tooth, to address function, failure modes, such as macro pitting, such as case crushing, such as tooth tip embrittlement. There's going to be a presentation and a paper issued at the HMA Fall Technical Meeting, actually tomorrow, as we are recording this, that outlines a wide variety of case depth calculations to address various failure modes, and we're going to use that paper in the HMA committee as a basis of expanding our recommendations for case depth.
I may add, I just came out thinking, if you check with the Hertzen law, you will see that you could reduce a bit against these rules the case carburizing test. But if then you check for tooth flank breaking, then you will see that you have to increase it, because for that phenomena you need normally a higher case carburized test. So yeah.
If we look at the standard currently, we have a calculation for case depth based on contact stress, based on the load. And then we have a calculation for case depth based on, quote, normal, quote. Not exactly sure what normal is, but normal. And then we have another calculation based on heavy case depth. And when the user says, well, which one should I use? The standard answer I have. And now with the new edition, it's only going to get worse, that we're now going to have 5 different case steps instead of the 3. And that's basically where the experience in your application, the experience in your heat treat furnace control, and the experience that you have in your metallurgical quality can get you to find the optimal case depth to satisfy the application.
I think there are different levels of detail. So as a rough thumb rule, 15 to 0.2 times module is a good starting point. If you go more in detail, you need to look at the radius of curvature, not the module, and look at the stresses and the residual stresses and hardness profile. And this is done in the calculation for the flank fracture in ISO. So when you go deeper and deeper, you can get very exact answers. But as I understood the question, what is the thumb rule? The thumb rule is 15 to 20.
All right, thank you. How can the efficiency of a gearbox be increased? What parameter has the largest impact? Don't say yes.
How much time do we have? Efficiency is a very interesting concept because there are so many levers that you can pull, and some are going to have a huge impact. And basically, the first one that comes to mind is oil viscosity and oil level. You know, if you have a gearbox that's full of oil, you now don't have gears anymore. You have paddle wheels, and you're now trying to throw the oil all over the gearbox, thus creating windage losses and heat losses and friction losses. So probably your first level is looking at your oil. Your second level is looking at your tooth geometry to see, to minimize the friction coefficients by either polishing or by grinding or honing. Then you start going into microgeometry, and then you go into all the other things that cause power losses, such as bearings and so forth. So, you know, in trying to improving efficiency, again, it also depends on what you're trying to do. I mean, there are boxes that may be transmitting, you know, 20,000 horsepower that you don't worry about efficiency on. There are others, such as electric vehicle transmissions, that's absolutely critical, because if you don't have a highly efficient gearbox, you're going to be in the middle of the desert when the batteries run out. So, you know, in terms of efficiency, I would tend to start looking at lubricant, I would tend to start looking at surface finish, and I would tend to start looking at trying to minimize the amount of oil you're flinging around in the gearbox.
It's reasonable for me.
Sounds reasonable.
Yes. So it's
In my opinion.
First thing is the oil, the lubrication, if it's injection or oil bath and the level. That's the most important thing.
Okay, thank you. What design parameter has the largest impact on micropitting?
approach we follow in ISO standard is that the film thickness in relation to the roughness is the critical path to micropitting. So everything which reduces the roughness or increases the film thickness will help against micropitting.
And the add-ons, no, which you have in the oil, because we measure the torque level on the micropitting level in the oil, and this is very important. If you have a good gear oil, or if you have hydraulic oil, it's a big difference.
The other item to be concerned with micropitting is the surface asperities, or the peaks and the valleys in the tooth flank, and how many do you have, and how sharp they are, and how tall they are. And, you know, studies have shown that if you can get rid of those high peaks, you're not going to get micropitting, or you're not getting micropitting as fast. Lubricant is important, film thickness is important, asperity fatigue is important. You know, is there the magic bullet? Don't know yet. I think there are certainly a lot of experts in the field who've been looking at this issue, and there's certainly a significant difference of opinion in terms of, is it this method or that method, or what is micropitting? Mm-hmm. In the early 1980s, we didn't have micropitting. But now we have micropitting. So what changed? What changed was they took the lead out of the oil. They changed the additive package, and all of a sudden, designs that worked didn't. And it annoyed the heck out of gear engineers, because, you know, what changed? And then we've been doing a lot of research and a lot of experimentation since then to try to figure out how to get the magic back in to eliminate and control micropitting.
In my theory also, I discovered the same. In the past it was not there, and suddenly in the late 90s everybody had micropitting. Now the automotive industry starts to get micropitting, and one reason in my explanation is also film thickness. They tend to go to low viscosity oil, lower and lower and lower, and therefore also the relative film thickness reduces. The load gets higher, Trim thickness also smaller, and this is driving micropitting too. Plus, the additives have a significant influence, yes.
Maybe this test for micropitting of oils should give a number for the load stage for micropitting. And we see a lot of oil companies which don't publish this factor because I think they didn't measure it. And we should make a lot of pressure that they get it because it's an important information. And it's a lot of, we need more oils where we know what the stage is.
Okay, thank you. Now, Frank, you talked about the asperities and the highs and the lows. Can super finishing the teeth eliminate micropitting?
Eliminate is a very strong word. There have been experiences in the field that if you go in and manage your asperity heights and basically planarize the tooth surface, so that's not making it absolutely smooth, you've just knocked all the peaks off. You still have valleys, but studies have indicated that if you can planarize your surface via super finishing, you're probably about 95% along the road of not having micropitting. The challenge becomes not all gears are super finished. You can't super finish everything. And for some applications, you may not have to worry about micropitting because you're going to fail some other way, or you're so lightly loaded that you're never going to stress the gears to the point where you have asperity contact and asperity welding. So that's been my experience.
Is there such a thing as having the teeth too smooth?
Hard to say. I remember very early where people were just starting to trying to get mirror finish and absolute flat, no asperity contact, no peaks and valleys, and they'd throw them in a gearbox and they do one rotation, the teeth would weld. And I've never been able to find any additional background data on that to see, can teeth be too smooth? I mean, one of the statements has always been, well, you want some pits in there for oil pockets, and I don't know if that's an old wives' tale or something along those lines. But I would say at this point, I think the jury is probably still out on can it be too smooth? But certainly smoothness will help you in terms of efficiency, in terms of noise, in terms of microgeometry control.
Exactly the same. I have heard about, but in our tests, current tests, we never saw too smooth. Also, my experience with race gears, which are extremely polished and very smooth, they didn't have any issue with lack of oil sucked into the contact. So some put dimples in the surface to get the oil into contact, but I think I have not monitored any occasion where this would be required.
Is there an official standard that is used for assessing the risk of micropitting? Official standard to assess the risk of micropitting?
336. It's not a standard. It's a technical report, a technical specification. But yes, it's there.
Okay. In which case is the pressure angle of a helical gear set different in the operating condition compared with the nominal values from the gear design? I can repeat. In which cases is the pressure angle of a helical gear set different in operating condition compared with the nominal values from the gear design?
When you change the diameter, when you pull, the angle will be higher.
If nominal means reference diameter, then it's clear. We are on another. The operating pitch diameter depends on the center distance and the tooth ratio only, and the reference diameter depends only on the modular and helix angle and number of teeth. So it's two different things, and if they are different, then the angle is different. Yeah, it's
Okay, thank you.
maybe question was something else, but
I've got a couple more for you guys. Worm and worm gears from different manufacturers can cause problems when mating them. Why is this, and what do I have to look for in order to avoid those problems?
Part of the challenge is in worm gearing, there is very little standardization for tool and tooth profile. And worm gear ratings, at least on the AGMA side, for many years was just a very large interpolated table, which many engineers hated because they had to raise something to the 2/3 power and they didn't have a calculator to do it. So worm gear ratings was a bit of more of an art than a science. And I think the geometry between manufacturers, they just tended to drift away from each other to their area and their area of, well, we've tested it this way and it's worked. I know in the ISO documents there are, I believe, 6 different worm tooth forms. And the challenge becomes, A, you have to make sure that manufacturer A is using tooth form, ZK versus ZA versus ZC. And then you also have to deal with the fact that, there isn't a standard, 5 diametral pitch for a worm, and it tends to be on a custom basis, and you get drift. So, whether you have a worm set or a spur or helical set, it's usually best, if you're making the worm, make the wheel from the same place. You're making the pinion, make the gear from the same place, because then you've guaranteed mesh compatibility, and you don't run into tool issues.
The other side, there are examples, companies buying worm and worm gear from different companies and mating them. So it's challenging, definitely, but it's not impossible.
classical worm gears with bronze on the gear, they run in quite easily. So a certain amount of error is gone. But I absolutely agree with you, because you see a manufacturing design for the worm. Normally, it's just module and tooth number, and how you do it, nobody cares. And we should care.
I have one last question for you guys. Why do splines have involute profiles in spite of the fact that there's no relative motion between the two members?
Answer. Clearly, involute is basically not needed, but it's the same process as when you cut gears. So you have your cutters and you do it, and you don't care.
So it's easy.
And it's working. It's working nicely.
Straight flank cutter for any number of teeth. So one simple tool for any kind of same shape spline.
Okay. And are there any standards that are commonly used to design splines?
The design, yes, it's DIN 5480, and the calculation according to Niemann, Winter, Höhen, Stahl is now the name of the machine element book. It's standardized there, or a rule given there, which is widely used in practical application.
But there is no strength calculation available as standard.
It's a standard as a real standard.
Yeah. Okay.
And their spline committee are working on a standard or an information sheet on splines. Some of the pioneering work in spline ratings in the United States have been done by Daryl Dudley in the early 50s, maybe. And there was a paper presented at the 2019 Fall Technical Meeting on spline ratings and some history, if you want to look at some background, both from the European perspective as well as the American perspective. But there are standards on the shape of splines, on tooth thickness of splines, accuracy of splines, nothing really on rating.
Okay.
I think this, if we talk about new standards, I think the German dean, they started a project 10 years ago, I remember, to do a calculation, and it was never finished. So it was a project. We got a pre-sheet, and it was partly even written by hand. I never saw something like this from Dean. But then after that, it was gone. No, nobody. We implemented in the software, but but I think that there is some need to do that, and mostly the KH beta factor, the load distribution can be very critical. Crowning, how to do it. So I think that I know also of some work in this camp. This could be one of the, maybe we can discuss tomorrow. No, Friday. I don't know if it's working group 6, but I would not know which working group because it's strength, not geometry.
Very good. Thank you very much, gentlemen. I'd like to thank all of you for joining us today for Ask the Expert Live. You can also view other episodes on Gear Technology TV, geartechnology.com/TV. Thanks for joining us, guys.